Okay, so next we have Kate Alexander from University of Arizona with us about recent developments and radio observations of TDEs.
All right, cool. So we'll continue the TDE observations session this morning. And we're going to move from the optical and X-ray part of the spectrum to the other end of the spectrum and talk about what we know about radio properties of these same TDEs. And we've also had a lot of very exciting recent developments in this field, in large part due to the increased sample sizes from ZTF that Subi was just telling us all about. So yeah, so it's a really exciting time here too. And like in the optical, we're starting to see an increasing diversity of behaviors in the radio. Some of them we definitely still don't understand. So some of this is, work in progress that I will share here. There's also a lot more. So if you are curious after my talk about weird radio behavior in TDEs, come talk to me. I'm happy to talk more about all the weird things we still are learning. So yeah. So I also wanted to start, like Subi did, going back to this diagram from Martin Rees's 1988 paper to really set the stage for why do we care about radio observations of TDEs. And as this sort of toy model shows, one main reason we cared is that they're really excellent probes of accretion processes onto black holes. You can think of a TDE as kind of a controlled experiment where you dial the accretion rate up to very high mass fallback rates. You exceed the Eddington limit with the mass fallback rate, as Subi mentioned, for most of the black hole mass range, and then it'll fall away as t to the minus 5/3. So over a couple of years, you can really do this controlled experiment in a variety of supermassive black hole environments. Look for state changes in the accretion flows. In particular, the peak is interesting because the mass fallback rate is super Eddington. As we heard from Brian yesterday, that doesn't necessarily mean the accretion rate onto the black hole is super Eddington, but it tells us interesting things about how black holes grow when matter is falling onto them quickly. And we know that black holes must have done this at various points in their lives, but it's still a poorly understood process. So it's nice to be able to kind of probe it in detail. So, we know outflows are generally produced at various accretion rates onto black holes. So TDEs give us a nice way to study, what conditions are needed to produce relativistic jets or maybe non-relativistic wind-like things. As I'll talk about, it turns out relativistic jets and TDEs are rare, although we see a lot of jets in AGN. So we'd like to understand why powerful relativistic jets and TDEs are so rare. And then because you have outflowing material, it's also interacting with the ambient medium that's already there. And so you can use these outflows and their interactions with the environment to learn more about the environments right next to supermassive black holes. I say right next to as an observer, I mean within, say, a parsec of the black hole. Maybe for theorists, that's not really right next to the black hole. But anyway, it's still very interesting and something we can't do for most of these galaxies at this distance otherwise. So why do we want to look in the radio for mass ejection? I always like to show this picture to illustrate it very dramatically. So here's a nice optical image of a fairly normal quiescent galaxy with Hubble. As you can see, the optical light is really dominated by the stars in this galaxy. And so if you wanted to study the black hole at the center, you'd have to figure out how to subtract all that pesky starlight out of the way. If you look in the radio, it's immediately obvious that not only is there a black hole at the center of this galaxy, but it's producing these very dramatic jets. And these jets are showing up very nicely in the radio. So if you want to study the mass ejection from the black hole, it makes sense to do it in the radio. What's the physical process that's actually producing this radio emission that we're seeing? Well, as this jet is moving outward, this material is moving very quickly. There's a shock that gets created between this outflowing material and the ambient environment. Or there's also shocks that get created within the jet between material moving at slightly different speeds. As this shock is formed, it enhances magnetic fields, which can then accelerate electrons to relativistic energies. You get synchrotron radiation. And that synchrotron radiation produces a non-thermal broken power law spectrum, which for the environmental conditions we see in TDEs typically peaks in the millimeter or radio part of the electromagnetic spectrum. Nice thing is synchrotron is a really well understood physical process. So if you can take observations at multiple frequencies or multiple wavelengths, and you can measure this spectrum and how it evolves over time. You can actually then tie that to physical properties of the outflowing material that is producing this synchrotron radiation. So you take observations at multiple frequencies, you can get the energy of the outflowing material, you can get the density of the environment it's expanding into. You can learn more about shock physics and how particles actually get accelerated in shocks by having various parameters like the fraction of the energy that ends up carried by these relativistic electrons by the magnetic fields. You can really start to probe all sorts of interesting physics, which then can feed back into your models of, how are these jets launched? What is this black hole doing in the first place? And so as an observer, I always really like to show it's really nice when our data fits the models really well. So broken power law fit with some very nice radio data here. This is from one of our star radio TDEs known as Swift J1644 plus 57. This was a jetted TDE discovered way back in 2011, but we fit each one of these multi-frequency radio observations over this data, and this paper covers a period of about 7 years, I think. You fit each one independently, you can get an estimate of what all these physical parameters are doing at each one of these snapshots in time, and then you can see how these different physical parameters evolve in time. So one interesting result from doing this analysis for this TDE was that we saw an increasing amount of energy in this radio emitting region with time. So the energy increased for about 100 days, kind of leveled off finally at this flat plateau-like value. You can come up with different physical explanations for what causes this increase of energy, but one idea that was presented in this paper is that you initially had an outflowing jet with material moving at a range of speeds. And so initially the jet was moving relativistically. The very fastest moving material started to slow down, allowing slower moving material to catch up and also shock. And so then you're basically seeing the energy carried by more and more material until finally, you're seeing everything there is to see, and that's why it kind of plateaus eventually. So you have to sort of keep tracking this source over a long period of time to eventually build up a full understanding of how much energy is in this jet. And this is quite an energetic, jet here. I think in this paper, we came up with an energy of a few 10 to the 51 ergs carried by this relativistic jet. Other fun things we did with this particular event, it was in a distant galaxy, tiny little thing at redshift 0.35. The big circle is what we originally had for a localization of this transient. It was originally seen in the gamma rays and X-rays with Swift until people thought it was a weird long gamma ray burst until we realized it wasn't. But then people did very long baseline interferometry radio observations that really helped pin down that it was associated with the center of this galaxy, helped convince us it was a TDE, even though it was like no TDE we'd ever seen before. As I said, it started out as a mildly relativistic jet. You can, as you do this equipartition modeling, one of the other parameters you can get out is the jet velocity. And so you can see it was initially mildly relativistic, took it about 700 days to slow down to the point where it was moving at non-relativistic speeds. So very energetic jet, slowed down over a long period of time. At late times, now that it's moving non-relativistically, you should be able to see any jet, and we could see this jet from very early times because it was pointed right at us, but we should have been able to see it no matter which direction it was initially pointing by about after 700 days. So that's kind of an interesting number to keep in mind when you're thinking about looking for these sorts of transients in, say, radio surveys. So when I started working in the field of TDEs, this is what we knew about them in the radio. After Swift 1644, everyone got very excited about looking for jets in other kinds of TDEs, and we quickly realized that it was not going to be every TDE that launched a powerful radio jet. There were a lot of upper limits at late times. So again, even if the jet had been pointed away from us, we should have seen it at late times, and there were all these upper limits. So we already sort of had this idea that jets and TDEs were something special. They weren't completely ubiquitous. And then, in the 5 or 6 years after that, we had more sensitive radio telescopes, and we started finding more TDEs. So we started being able to probe fainter radio luminosities, and we started to see that there was actually a diversity of radio behaviors in TDEs. So there aren't very many that produce extremely luminous radio emission, but there are quite a few that produce lower luminosity radio emission. And so then the question we asked is, well, okay, what kind of model do we have that could give us such a wide range of radio luminosities? What's really going on in these radio faint TDEs, is it one process or several processes that can produce radio emission at these lower luminosities? Are we maybe seeing non-relativistic material as opposed to relativistic material? That's what doing this kind of analysis of the synchrotron radiation seems to suggest, but then what does that mean? So we really decided to focus our efforts on trying to systematically follow up every newly discovered TDE in the radio and trying to understand, what's producing this radio emission. And people have come up with various ideas. And I think it's still an open question, which of these processes are, which one or which multiple of these processes are producing the radio emission we do see in these fainter radio TDEs. One idea is during the circularization process, when the debris stream is coming back and colliding with itself and eventually producing the accretion disk, you can have these stream-stream collisions, which might be energetic enough to launch outflows. So that outflowing material could be the radio emission we see. You could still have a jet or maybe some kind of more spherical wind, but maybe it's just much, much weaker. So maybe it's not a problem of different processes. Maybe it's just that some jets are much more powerful than others. So radio emission in TDEs has also been modeled with some kind of, accretion-driven jet or outflow kind of like this. There's also this idea that maybe the radio emission has nothing to do with the accretion onto the black hole. Maybe it's the other half of the story. So as we saw in the diagram Subi showed, about half of the material in the star is ultimately gravitationally unbound from the black hole. It never ends up accreting, it just gets flung off into the ambient environment. And so that's also material that can be moving quite fast, and it's going out and interacting with the ambient medium. Julian Krolik and others proposed, well, maybe that's producing the radio emission that we see in TDEs. And again, there's a lot of debate about exactly how bright the radio signature from these various processes should be. But really what we need to do to try to understand which one or ones is producing the radio emission we see is to get a larger sample. We need to do detailed studies of individual events. So, for example, as Subi showed, we have some really nice light curves from very early times for some TDEs. We can really then, if we have a well-studied radio observations as well, pin down, when was the radio outflow launched relative to peak optical light. Some of these models might have different time scales. So doing these sort of detailed studies can really help. But we also want to systematically do radio follow-up of all nearby TDEs. For instance, if it's the unbound stellar debris, that should exist in every event. So we might expect all TDEs should show radio emission at some level. But if it's an accretion-related process, well, maybe not all TDEs reach super Eddington accretion rates, particularly the ones from more massive black holes. So if we don't see, if we see some mass dependence in whether a TDE has radio emission or not, if we see that not all of them do, maybe that means that one of these other models is more likely to be correct. So well-studied individual events, rates, those are the two sort of big questions in 2020 that we set out to try to answer. And so we've been really trying to go after this, again, taking advantage of the enhanced TDE discovery rate. So we've been going after every new TDE identified at a redshift of less than 0.1 within the Northern Hemisphere with the VLA for the past 3 years now. And mostly this has been optical events because we've been trying to go after things that were announced fairly promptly to the community, but we have looked at a couple of X-ray events as well. And so we've just, been, every time there's a new TDE, we go and trigger VLA observations. If we detect something, we start observing it in detail at multi-frequencies. If not, we still come back a few months later and check again in case there's delayed emission that turns on later. And so we're sort of, right now, still in the data collecting stage of this whole process, but we've started working on papers on individual events. And then, in a year or so, when we've finished collecting all the data for the sample, we'll be working on our papers for the whole sample that tell us things like what is the actual rate of radio faint emission within the first year after disruption for these TDEs. This is an international collaboration involving a couple of people in this room as well as others. Telecons for this project are really fun because we are scattered all over the globe, but it's been really a lot of fun to work on this project. Now, the preliminary results is that it does not seem that all TDEs produce radio emission within the first year of their lives. It's maybe more like a third, although we still have some TDEs here that are in this red portion. This is either because they're things we've only looked at once so far, so I can't tell you yet whether they have variable emission, or some of them have pretty constant radio emission that we think is probably coming from some unrelated process in the host galaxy, because it's not changed over a period of a year or more. And so it's probably not really related to the TDE. And so we've been announcing our results publicly. Yeah, it's a very exciting ongoing project. We try to keep an up-to-date list of what we've looked at on our program website in case anyone else is interested in collaborating or hearing about, if you can use radio data on an individual object, we're happy to talk. We're open to collaborating, and then eventually we'll also publish everything that doesn't get its own paper in our sample papers. So I wanted to talk a little bit about two objects that we've discovered in this program, just give some preliminary results, and then after that, I'll talk a little bit more about some things that don't fall under the scope of this program that I also think are interesting, outstanding questions, and then we can have discussion. But one of the objects I'm most excited about that we've observed in the VLA large program is called AT2022 CMC. It was discovered last year. It's the most distant TDE yet that we've ever seen by just a little bit. It was excitingly discovered in an optical survey. So the jetted TDEs we'd found previously, we found them on the basis of very bright, variable, weird gamma ray emission, but this one was discovered as a fast fading optical transient, which is really cool because that may be a more reliable way of finding distant TDEs. The gamma rays might get attenuated before they reach Earth. And so this is potentially a way to find more jetted TDEs, which you really generally find at large distances just because they are so rare. And DJ had a very nice paper about doing some multi-wavelength modeling of the early broadband emission from this source. We find that the radio is consistent with synchrotron emission from an on-axis relativistic jet. So kind of similar to Swift 1644. The X-rays are then inverse Compton from this synchrotron photons that's been scattered to higher energies. And there's this little black body component in the optical. So the idea is it's a very narrow jet pointed right at us, and it's from this TDE. Although there are other possibilities that have been proposed, but I'm pretty, it could also be some weird supernova based only on the early data, but based on the ongoing radio data we have, I'm pretty confident it is a TDE. So we've continued to monitor this. This is just a subset of our very nice radio and millimeter data we've got for this event. We're still following it. It's still detected, although it is fading. And this modeling of the radio emission over the period of more than a year now shows, that it looks like an initially mildly relativistic outflow that's continuing to slow down. Interestingly, it seems to have decelerated more quickly than Swift 1644, perhaps was never quite as relativistic to begin with. It's already kind of transitioning into a more non-relativistic state only a year after discovery. So that's kind of interesting. That means it might have implications for how long lasting these things are if you're trying to look for them in blind radio surveys. And as I mentioned, we have an ongoing monitoring program, but we're also planning to, write this up soon. And, at this meeting were next month, I could possibly show you some more plots, but the results for this will be coming out quite soon, which I'm quite excited about. So yeah, it does, unlike Swift 1644, it's maybe, yes, it's pretty energetic. It's maybe not quite as energetic. So it seems interesting that the second well-studied jetted TDE is not a complete clone of the one we knew about before. There does seem to be some diversity within the population. So that's pretty cool. And yeah, happy to talk about that more afterwards, but I'm trying to sort of jump around and give a flavor of the different kinds of results. So we'll move on to the next one for now. The other TDE so far that's gotten its own paper from our program is this ZTF optical TDE called 2020 VWL. I'm sorry, I don't know the other name for it, the more fun name, maybe you do. I have to look it up. Yeah, it's one of the, I think it's one of the first ones from CTF2 or one of the last ones from ZTF1. It's right around that transition time. But we started observing it as one of the first targets for our VLA program. We started observing it in February 2021, and we've observed it for quite a while. It also has these nice synchrotron SEDs. Unlike 22 CMC, it was definitely not a relativistic outflow. It was moving much more slowly. Still pretty fast, 3% the speed of light, but that's kind of slow for these TDE outflows. So it seems to be, lower energy, kind of more typical to these other radio faint TDEs from that plot that I showed at the beginning. And so that is quite interesting. The other thing that's quite interesting is we have a pretty nice, because we're able to start observing this fairly quickly and track it over such a long period of time. And we have this measurement of what the velocity of the outflow is. We can sort of extrapolate backwards to roughly when we think the outflow would have been launched, assuming that it was moving at this speed throughout and didn't slow down. So this is a very rough guess, but it's interesting because the outflow has to have been launched pretty promptly. The other optical light curve is still rising during this time. So whatever has produced this radio outflow is something that happened promptly. It's not something that happened right around the peak optical light or later. And so again, there's lots of ways you can tweak these different models to sort of work with this time scale. But we suggested in the paper that perhaps there is a hint from this timing that something that happens during the circularization process might be more likely to be powering the radio emission we've seen in this particular TDE. Perhaps it's not related to a very high accretion rate, because if so, we shouldn't have seen the radio emission quite so early. So that's very interesting. Again, this is just one event as we continue to do these sorts of analyses for the other events in our program. And as we build up these larger samples, we'll find out how typical this is. But yeah, we were very intrigued by this hint, and we'll see where this goes from there.
Okay.
Yeah.
On that, I wonder, it's kind of hard to tell the time scale there, but if you wanted to compare, maybe this has already been done, but I wonder if it was from the unbound debris stream, then it would be launched a good bit earlier, and you could just like mark, like this seems to be very consistent with the initial rise, which does, I agree, like makes sense for stream collisions, but you could just see how much further it would likely be back.
Yeah, so I have to look at the modeling that's been done for this event, because I know there can be a variety of delays between the time of disruption and when the light curve starts to rise.
Right.
So,
Well, if you would, so if it's from stream collision, that's absolutely true, but you could assume like the smallest possible, and then,
Yeah, so I would be actually curious, because I assume you and others have also done, and I think I actually have collaborators done some MOSFET models of these things, but I haven't looked for this one, this particular TE, how long the delay would have been. So yeah, I think you can't totally rule out the unbound debris, but it would be interesting if you are very confident that in this one, the disruption happened much earlier, and then the unbound debris emission should have actually been earlier than this.
I mean, why can't it also be a jet?
So it could. We make no definitive conclusions in this paper. My point is just that a lot of the models for jets have sort of posited what if they happen during the very highest accretion rate onto the black hole. That's not necessarily the case. We know in AGN you can get jets with low accretion rates as well, but it would be a little puzzling to me to try to claim that this is a jet launched by super Eddington accretion, given where this is in the light curve.
It doesn't have to be super Eddington,
right?
You say, so.
Yeah, so that's what I'm saying. I'm saying some jet models might be disfavored by this timing. We stopped short of ruling out any of these models definitively in this paper.
And this one doesn't have any X-rays?
Subi, do you remember if this one has X-rays? I think it doesn't, or not bright ones.
It's VVM.
VWL.
I don't think so, but I can check.
Yeah, anyway, they, like I said, not completely definitive from this one event, but it'll be interesting as we build up the population to sort of see what the timescales look like. And also there, I'll talk in a minute about TDEs that show radio emission at later times, which of course could be a completely different physical process.
I mean, by calling it an outflow, you're already making the assumption that it was an outflow, not a jet, right? So maybe just the semantics, like you're already assuming it's an outflow. Yeah.
Well, I should clarify, I use the term outflow very loosely and all encompassingly. When I say outflow, that is meant to say it could be, I would consider a jet to be a type of outflow. And you can make, one of the free parameters, there's a lot of free parameters in these models. One of the free parameters is exactly what the geometry is. So what we will often do rather than, so you have to assume some geometry basically. And two sort of nice limiting cases to assume are perfectly spherical geometry and a really narrow collimated jet that stays collimated. And, but some of the parameters don't change very much, like the physical size doesn't change very much. So you don't get a hugely different assumptions about the velocity from assuming it's a narrowly collimated thing versus a spherical thing. So it's, the non-relativistic assumption is more robust. The energy, the total energy in the outflow can change a bit more depending on what you assume about the geometry. But again, it might be a factor of 10 change or something. It's, you can see, so this plot just kind of shows these, where all of these different events fall in terms of energy we infer from the radio analysis versus how fast the outflow is moving. So sort of low energy, non-relativistic things are over here. And then we have a couple of jetted events up here. So you're not going to move the inferred energy all the way up to the other part of the diagram. It still does seem to be something different from the really powerful jetted ones, but it could be a weaker jet. We are definitely agnostic to that point. But anyway, I like to throw up this plot just because, one thing I've said a couple of times is that really powerful jets and TDEs are rare. This is not the only kind of accretion onto a compact central engine system that we know of where this is the case. You can look at what happens when massive stars collapse to form new black holes. So if you have a star that explodes as a type 1c supernova, which is a supernova with no hydrogen, that often will just produce some non-relativistic, quasi-spherical ejecta that's thrown out during the supernova explosion. Very occasionally, it'll produce a collimated relativistic jet, which we see as a long gamma ray burst. And if you look at the rate of long GRBs, so the rate of 1c, 1b supernovae, it's maybe 1% of this type of stellar explosions successfully produces a collimated, powerful relativistic jet. And so you can sort of draw this analogy that whatever this process is that's producing jets in these newly formed stellar mass black holes, getting a jet seems to be about as rare there as it does on this accretion process on a supermassive black hole. So that's kind of interesting. As an observer, I throw out this posit to the theorists in the room. Are we learning something generic about accretion onto black holes? Maybe we'll have more TDEs soon that we can throw on here and see if this holds up. The other thing that's fun to talk about you can do with populations of TDEs is build up density profiles around the black hole. As your outflow moves outward, it's encountering a medium. You can see how the density changes as a function of how far away you are from the black hole. And you can build up these density profiles. A lot of TDEs seem to have pretty steep density profiles around their supermassive black holes, which is kind of interesting. This is sort of steeper than the density profile that would form if your black hole had previously been undergoing spherical Bondi accretion. We've posited that maybe before the TDE, there were sort of different accretion histories onto these black holes that might be driving these kind of different density profiles. So maybe this is telling us something about the previous activity of the black hole or other processes shaping the density in the ambient environment. Again, very hand-wavy, speculative, but.
Are there selection effects? I mean, are they throwing out AGN hosts when they're looking for TDEs?
Yeah, so this is another thing that we want to look into more when we have the larger sample. There was this interesting thing I noticed, when we had all 4 of these objects on this plot, which is a lot of the TDEs that had detected radio emission did have some other signs of low-level AGN activity. 14 Li's host galaxy actually had radio emission from an AGN before the TDE ever happened. So we were wondering, is there something about AGN environments that makes radio emission in TDEs more detectable? I would say that as we've built up a larger sample, I don't know that that's necessarily held up, although at some point I'll want to chat with Suvi and ZTF friends about the details of the host galaxies if they've gotten more detailed spectra than the plots of global properties that make it into the paper. It'll be interesting to think about as we're going through and doing our sample papers. So yeah, there may indeed be a selection effect, but it'll also just be interesting to see if that holds up when you have a larger sample. Yeah.
Isn't there also just a selection effect of lots of gas at small radii means it's radio bright?
Yeah, exactly. Exactly. And I mean, maybe that is why we see that so many of them are steep as opposed to, if there was a TDE in a lower density environment, then the radio emission wouldn't be as bright. So, yeah, EJ.
So I should point out that this only works, so this is where it's important to call it jet versus outflow. So if you're assuming an outflow, you're assuming something is propagating outwards. You can model the synchrotron with either internal emission to the jet
Yeah,
or an outflow, which is like an external emission.
yeah,
So this whole thing is only valid if you assume an outflow is propagating outwards. But this emission can also come from within the jet, in which case you're only probing the jet structure, essentially.
Right.
You're not probing anything about the external medium. It's only
yeah.
the
No,
internal
I should
medium.
also say that, yes, this model is assuming that you have, it's kind of like a gamma ray burst where, you know, you had some impulse of energy from the center and you're just tracing the outer part of the outflow or the jet as it moves outward into the ambient environment. So we're thinking of an external shock here. If instead you have a bunch of material moving at, you know, different speeds and it's more like an AGN jet where what you're seeing is the internal shocks within the jet, then yes, you do have, you know, you're not then probing the external medium. A lot of these, you know, radio light curves we've seen, well, to the limit of our data, they often appear to be quite smooth, but again, we don't actually have super high time resolution light curves for a lot of these TDEs. So there's could be variability on shorter time scales that we're missing. And I know for 14 Li, you know,
Yeah,
you
but
guys.
14 Li, you know, in fact, there's the X-ray radio correlation. And then this profile that you get is actually like perfect smack on with the classical like jet structure, like the R to the 2/5 is actually what, you know, Alan Marsh and those people predicted like 2 decades ago, how the jet should be. So anyway.
Yeah, I mean, a lot of AGN jets, you know, it's more of a flat spectrum because you have, you know, you're seeing the superposition of different synchrotron components as opposed to the single, you know, at least we've often said that the fact that you see this nice turnover and everything is in the synchrotronicity is sort of a sign you're only seeing it from one emitting region. But yeah, there's a range of possible models.
But if it's correlated with X-rays, it has to come from inside. It cannot be an outflow. An outflow is completely detached from what's happening really close to the black hole. So it's-
Yeah, I
it's
agree. This
completely-
model would, the external model would not predict a correlation with the X-rays. So
You mean
fortunately, we haven't gotten
temporally correlated?
Yes. So fluctuations in X-rays.
yeah, so we had hoped to be able to do a analysis of that with VLA, and then there hasn't been a X-ray and radio bright TDE in the last 3 years, so we've been kind of out of luck. But yeah,
One other interesting question of what's producing the radio emission is there's this class of changing look AGN where we think that they're, you know, have a big change in accretion rate. We don't know exactly why, but and I'm curious if there have been any radio studies of changing look AGN and if their radio properties are similar or distinct, because in that case, I don't think you'd expect them necessarily to be launched. Well, they certainly shouldn't have outflowing debris streams. But perhaps they're launching an outflow or perhaps a jet, but it'd be very interesting to sort of, do you know if anyone has studied them in the radio?
yeah, so I agree it would be a really interesting project.
Yeah.
It's not that I am aware of.
Yeah.
It's kind of something that been in the back of my mind, I haven't really had time to develop, but I think it would be a great project for a student or for anyone who's interested to take a look at. I mean, you could get started. So we now have the VLA Sky Survey, which is, you know, very low cadence, but if you just wanted to get a heads up as to which changing look AGN might have some radio emission, it could be very interesting to go look at the VLA Sky Survey data, which covers the whole northern sky. So presumably there's some good changing look AGN you could go look at and see if there's anything there, and then you could pose for more time to follow up some interesting ones. But I don't think anybody has, I'm not aware of anybody who has been, for example, obtained radio following during one of the changing, you know, the state changes, but I think it could be interesting. Definitely. I know there's some work being done. People are also blindly looking for radio nuclear transients in the VLA Sky Survey, and there's also a survey in the Southern Hemisphere called VAST. People are doing the same thing. And that's finding some interesting things, some things that might be radio TDEs, some things that might be other kinds of AGN activity. So there's some, you know, work that I'm not involved in that I understand is in prep and coming out, which I'll be very excited to see about sort of the range of radio behaviors of AGN. You know, when we started doing this for TDEs, you know, I looked at what had been done with radio variability of AGN and concluded most AGN are not very variable in the radio. So we're used to AGN, you know, and X-rays having giant flares all over the place, and the radio having a factor of 2 change in an AGN is a pretty big flare. But then there is this extreme tail of variability where it turns out some AGN also produce giant radio flares. So there definitely, as you were saying, there's a spectrum of accretion related behaviors onto black holes that will be very interesting to fill out in more detail. So I think we have about 5-10 minutes left or something. Anyway, the last thing I wanted to bring up for this group is this other interesting you know, new development that we've had in the past couple of years, which is another aspect of radio TE behavior that we don't fully understand. So this is also kind of a topic for discussion. So again, here's this plot I showed previously about, you know, we have all this radio faint emission, but it all seems to be sort of within a year fading away, fairly monotonic. So we kind of, you know, designed this whole VLA program to look at things in the first year and not beyond that. And then in part due to things like the VLA Sky Survey, we discovered that some TDEs do not actually finish doing everything they're going to do in the radio within a year. Some of them, in fact, show these really dramatic rebrightenings that can happen up to a couple of years later. And so, you know, these are 2 events that have been published so far, Assassin 15OI, which I'm going to talk a little bit more about because it's everyone's new favorite TDE, I guess. Also 2018 HYZ also shows this very dramatic, rapid rise to pretty luminous radio emission 2 or 3 years after discovery. And you should, I put at the bottom here, we're working on looking at a larger sample of TDEs kind of at timescales of about 2 to 6 years post-discovery. And this is a tentative number, but it's looking like, you know, this is quite common for TDEs to turn on at later times to some level. I think these 2 are probably the most dramatic examples, but the story is definitely not all over in terms of interesting things going on in the radio and TDEs. And so, you know, it's interesting hearing about how QPEs might also be something interesting that happens at very late times, probably completely unrelated to these radio flares, but it's clear that TDEs are long-term objects and there's interesting physics we don't fully understand going on in these events at late times. So I want to talk a little bit about Assassin 15OI, which is a project that a former grad student at Northwestern has been leading, Prajita Hajela. And she has gotten these very nice multi-frequency radio observations of 15OI during its 2nd flare, and also re-looked at the multi-frequency radio observations from the 1st flare that was taken by originally by Asaf Haresh and friends. And so our analysis of this radio emission, again, if you model it as this kind of external shock between some sort of jet or outflow in the ambient medium, show that it carries a fairly significant amount of energy. It's moving faster, you know, maybe not truly relativistic speeds, but, you know, pretty fast. Maybe mildly relativistic, fairly energetic. And we're still sort of exploring different possibilities for what could be powering this late rising radio emission. So I'm certainly happy to chat more with people here if this jumps out to you as having an immediately obvious explanation. One thing I did want to put up, since Brian told us all about his cooling envelope model for TDEs yesterday, is that if you look at the multi-wavelength data for 15OI, it actually qualitatively seems to agree fairly well with this cooling envelope picture. So here I'm showing the UV and optical bolometric luminosity of 15OI, and then when we analyze the X-rays, we find that you need 2 components to fit the X-ray spectra. There's a power law component and a black body component. So those are both shown here. The black body component, as Suvi mentioned, is delayed relative to optical. So it you know, increases until a couple hundred days after and then falls off. So in Brian's model, the X-ray luminosity is kind of tracing the accretion rate onto the black hole. And so, you know, this would be roughly the fallback time for 15OI. And then you can see sort of around that time, it starts, the optical luminosity starts decaying as t to the -3/2 roughly. So that's again sort of consistent with this picture. And the envelope kind of gets into this sort of self-regulated phase where the accretion rate is peaking. And again, that's about where the X-rays peak. And then at some point, the envelope will be completely accreted. So, then this is this idea in his model, that's roughly when you'd have the time scale of a disk forming. And, if you did have some sort of disk-driven outflow or jet, it could be launched around that time. And so this down here is the radio light curve. So there's two flares in 15OI. There's this first one that peaks around 100 days, and there's this other later one that we see show up around 1,000 days. Unfortunately, we don't have any radio data between here, so we don't really know if it started at 1,000 days or a bit earlier. But if you had some sort of jet that was launched near the time of peak accretion, it might take that long to decelerate so that we could see the radio emission. So in a very, again, kind of hand wavy sense, you can maybe tie this second radio flare to this sort of delayed onset accretion in this model. Then you still need an explanation for the first flare. Maybe it's something related to the circularization process, which is really not captured in this cooling envelope model. This cooling envelope model really takes over and explains the behavior starting around the time of this initial line. So again, this is work in prep. If people have thoughts on this, I'd be very happy to chat about it more, but we really were excited about 15OI because it's one of these, it's the TDE with this interesting late time behavior is the first one really published that displayed this behavior, and we're starting to use it as kind of a canonical or a case study to sort of dig into this more deeply from a multi-wavelength point of view. And I do think, that's sort of the final point I'll make maybe, is that TDEs really are multi-wavelength transients. And I think the radio provides an important piece of the story. So if you really want to try to understand these very complex physical processes that are going on, then incorporating information together from the radio with other wavelengths is really going to help you get there. And I think that's about everything I had to say, but I'm happy to have more discussion now. And then we also have a discussion in the afternoon, so we can talk more about some of this stuff then.
Two questions during the talk. I think we'll take a few now and then go to coffee break. So we can also continue then. Adam?
So for 15OI, for the last X-ray, which instruments are these X-ray observations taken? So you're getting the drop off in the power law.
Yeah. So this is also something we don't quite understand is why this is dropping off so quickly. I believe we had some Chandra data and some XMM data. So I think that's where these 2 points came from. Maybe one is Chandra and one is XMM, or either both. XMM, yeah.
So that would be weird if it's the same instrument and you're still seeing the drop off.
Yeah.
Because I think the power law component was always weird. It's that fixed normalization despite the soft X-ray brightening.
Yeah. So we were, so that's definitely something we want to try to make think about a little bit more, because is how do you get the power law component in the first place? I mean, you could be, it could be Compton emission, but what are you Comptonizing? Is it some, photons from the optical UV that's being upscattered into the X-ray band? Is it something else? Is it kind of this corona-like component? Or, if it is emission coming from right near the black hole, then how do you get that emission to go away at late times when you should be, finally seeing the accretion disk? I'm very interested to hear what people think about that.
Yeah, I'm sure this is a remarkably stupid question. This is very, very interesting stuff. I was struck when you were looking at the radio energies, how your very high ones were often not very flat and non-evolving, whereas your low energy radio did all these funky behaviors. And it got me wondering what the natural state in these systems might be independent of the TDE. And is there, any argument to say that if we look at the orange curve here in this case, for example, that the natural, it might be evolving to what is its natural radio state over time, and that at early times, for some reason, the TDE was involved in diminishing what is responsible for the the radio emission and that comes back at, more further away from the event?
Yeah, so for some of these TDEs, we do have upper limits from previous all-sky surveys that NRAO did 20 years ago, like the first survey. And they're not very deep, but if 15OI was producing radio emission as bright as the second peak, we certainly should have seen it in that survey, and we don't. So I mean, it's not super constraining, but it is, it can rule out really bright archival emission. And for Cessna 14 Li, we actually did see some radio emission in the first survey. So that was part of why we were so confident that there was an AGN contribution in that galaxy. But now for future TDEs with the VLA Sky Survey, we're going to have better constraints. The VLA Sky Survey's factor of 5 or 10 more sensitive than the previous ones. And so it's starting to really get down to interesting parts of parameter space. So we'll be able to, for future events, have a better sense of what's going on. So for 2018 HYZ, for example, we looked in the VLA Sky Survey and there wasn't anything before it turned on. We'd actually, we had a pretty tight constraint on the rise because we had an upper limit right before it started going up also. So it does seem like whatever this is, it's not maybe the prior state to the black hole. Brian, I see you have your hand up on Zoom.
Thanks, Kate, for the talk. I wanted to go back to 22 CMC, where you said you had some new indications that you were more confident it was a TD. I'm not actually strongly questioning that it's a TD. I think one of the mysterious aspects of that event we raised with Tatsuya was the fact that the X-ray, emission and the energy injection phase we infer was very short. It was like 1 day.
Yeah.
And then the actual optical was several weeks. So I think there's a bit of a mystery in the TD interpretation as to why the relativistic jet would be on for such a shorter time than what would nominally be the fallback time or nominally be the optical time. So I guess I'm curious what your information is, or that you think that you're more confident it is a TD versus some kind of unusual supernova or something like that. So.
Yeah, so there's a couple of things. One is just, I know the model in your paper was sort of predicting the radio should continue to just sort of drop off pretty quickly, and we don't see that. So it does seem to stay brighter in the radio than that particular model would suggest. And I'm sure there's probably ways to adjust the supernova model so you could have a slightly longer lasting radio emission. So maybe that's not completely conclusive. We've also been monitoring the X-ray light curve of 22 CMC. And it was detected with Swift XRT for a while. Now it isn't. We got some data with Chandra that also is an upper limit. So because it's further away, it's not going to be as conclusive and abrupt shut off as we're able to see for Swift 1644. But I think we can say with this upper limit, we do see a pretty significant drop in the X-rays.
I see. Okay.
So I think we do see kind of that same sort of
right.
Maybe, although again, we'd have to kind of, we're working on a paper now, actually. Tarne Akari is going to lead a paper on the X-rays behavior.
The X-ray light curve, maybe that'll help.
Oh yeah, I could show the light curve. Hang on 1 second. I'll have to.
I mean, just to give people some context, these previous jetted TDs showed a remarkable shutoff in the X-rays around the time you'd expect the disk to be becoming the fallback becoming sub-Eddington. So it's like the jet is really turning off in some kind of state transition. And so if you saw the same behavior, I agree that would.
You want me to share?
Oh, if you have it up, then sure, go ahead. I'm just finding it.
I agree that would be suggestive of a supermassive black
there you
hole.
So here's the previous one, 1644, it just shuts off.
Yeah.
And then here's the previous second jetted TD, same thing, shut off. And this is 2022 CMC.
Okay, so.
Yeah, so again, it's not quite as dramatic, but it does seem to be statistically significant that the upper limit is below the extrapolation.
Right. Sure, thank you.
Yeah, thanks, DJ, for having that ready to go on the show.
Okay, so I think we can continue with more questions over coffee. So let's thank Kate for this again.